Assalamu alaikum. Uh, in the previous class, we discussed a bit about transients, and we assumed that the circuit is an RL circuit, and which is supplied by a voltage source, whose voltage is given by root 2V sine of omega t plus alpha. This was the expression for the voltage. Now, same thing when we do the different analysis, we uh, calculate its current by writing the differential equation and solving it. Its total current was given by root 2 V by Z sine of omega t plus alpha minus theta plus root 2 V by Z sine of theta minus alpha e raised to minus t by tau. In this case, this is the voltage waveform which is drawn by a dashed line, and this is given by root 2 V sine of omega t plus alpha, and it is leading to this reference, where reference is taken as t is equal to 0, and this reference is nothing but the switching at. This is the point at which the circuit breaker will will close, or we can say we are forcing a current to flow in the circuit. And before, there will be no current. Before t is equal to 0, there will be no current. That's why we call this alpha as a switching instant. So since current will be 0 at t is equal to 0, because it's an inductive circuit, and this current will be the steady state part of this current. It will be equal to root 2 e by z sine of omega t plus alpha minus theta. Its magnitude will be equal to root 2 v by z maximum value. That means this will be equal to root 2 v by z, and it will be lagging and this current will be lagging to this voltage by theta. That's why the difference between angle between this point and this 0 of the voltage and current will be theta. That is shown over here. So this will be the steady state part of the current, and this will be the maximum value, or we can say value of the current at t is equal to 0. This has to be interrupted. To make it 0, a DC offset current will flow through the circuit, which makes this current to be equal to 0. So this DC offset, that is whose expression is given by this, is shown like this, and its decaying is very fast as R is present and has a finite value, because we are assuming in this case it is an RL circuit and R has a finite value, and its tau, that is R by L, will be very very small, and it will decay very fast. So in that case, when we add up these two, DC decaying component and this steady state component, we get the actual current, that is this. This will be the actual current, and it will coincide with steady state as DC decay will decay off to 0. And this is its expression. Now coming to this, I have told you that we can make this decaying or DC component equal to 0 if theta is equal to alpha or alpha is equal to theta. In that case, what does this mean? It means that we'll not switch the circuit breaker on at this instant. We make this voltage to change from this instant to this instant, so that this alpha will be equal to theta. This is nothing but we are just waiting for time to elapse so that voltage will change from this point to this point, so that this alpha will be equal to theta. In this case, you will see that this is the steady state current of the total current, and this is the voltage. Since the value of current at t is equal to 0 is 0, the steady state value of the current at t is equal to 0 is 0. That means the DC offset current has to be 0 to make it equal to 0. It is already 0. There is nothing to be added or subtracted to the value to make the current equal to 0. In this case, you will see that it was a negative value of the current. To make this negative value equal to 0, it draws a current magnitude of this whose value is positive and whose magnitude is equal to this, so that net current will be equal to 0. Here the current is already equal to 0. It will not draw any current from the any DC current from the system. So you will see that from this explanation also, this DC decaying component will be 0 and the voltage and current waveform will be like this. So you can put it here. If alpha is equal to this theta, this component will be equal to 0 and the total expression of the current will be given by this root 2 V by Z sine of omega t plus alpha. There will be only steady state component, there will be no transient component, and this it will be equal to root 2 e by z sine of omega t, and this omega t, that means it will be exactly in phase with the, it will start exactly with respect to the reference. That's why it is lagging or leading will be equal to 0. Now this is the case when theta is equal to alpha. Now coming to this worst case condition which we have discussed earlier, in that case we assume that is the doubling effect. And when worst case condition is taken, it means alpha is equal to 0 and theta is equal to 90 degrees. That is x is greater than r, which implies r is almost equal to 0. We can say that it is a purely inductive circuit. In this case, tau will be equal to L by R. Since R is very close to 0, it will be very high. You can see when R is equal to 0, tau is infinite, it is very high. Very high means it will take a lot of time to decay. It will always be there. So taking of DC component will be very slow in practical. We cannot say that it will be infinite, but it will still decay, but it will be very slow. That's why I have shown this DC decaying component not decaying fast. So here alpha is 0. That means this is shown alpha is 0. This Vt will start from the origin, from this reference, and this will be our voltage waveform. This dash will be our voltage waveform, and since theta is 90 degree, it means the voltage and current will have a phase difference of 90 degrees. So this will be the current, that is steady state current. This will be the steady state current will be like this. And as I have told you, this will be, since at this point it will have a maximum value. The current will have a maximum value at the starting at t is equal to 0. It will have a maximum value. You can see that this is coincident to this, and in earlier case it was not a maximum value. Here it was not a maximum value. Maximum value would have been somewhere over here. Here this value at t is equal to 0, it will have been definitely less than maximum, but here it will be exactly equal to maximum value. That's why I have written it Imax. So to make it 0, it has to draw a positive current of same magnitude to make the total current equal to 0, because initial current has to be equal to 0 because of the inductive circuit. So it goes like this, and its decay will be very slow. Now this is the total current. It will definitely be summation of this current, steady state current, and the transient current, or we can say DC decaying component. Now this will be total current. You can see it will be like this. It will be like this. If R is equal to 0, it would have been a straight line like this. There would have been no decay. But practically R is not equal to 0. It is very small. There is small decay. That's why you will see that there is some decay, and this also, the total current will also go to negative because this is not maximum. If it would have been maximum, this would have been directly touching to this. It would have a waveform. Total current would have a waveform similar to this full wave rectification. So what I mean to say is, here you will see that this is the maximum current that will flow through the circuit breaker. This maximum current will be equal to, you will see that this is maximum total, this will be also maximum total. It will be equal to 2 times I maximum. This is actually shown like this, 2 times I max, this plus this. Of course there will be small decay from here to here. When we assume R to be very high, R to be infinite, the decay will not be so much. In that case, from here to here, the total current will be twice Imax, that is 2 root 2 V by Z, that is doubling effect, which we have already cleared. So in general, we can say that by turning on the circuit breaker, we should always turn it when current will be equal to 0. That means this current is equal to 0, or we can say the steady state part of the current is passing through the 0. natural zero, like the earlier case we had discussed, this one. In that case, there will be no transient. And in case of worst case condition, in case of the worst case condition, it will be, this current will be maximum, or we can say DC decay component will be maximum when the current interruption, or when the current or we can say when circuit breaker operates, when this is when the current steady state has a peak value. You can see it here, steady state current has a peak value. In that case, it will have a worst case condition. The total current that will flow through the circuit breaker will be maximum, that is 2 root 2 V by Z. With respect to voltage, we can conclude this, uh, we can conclude it that whenever voltage, whenever the switching takes place, if voltage is at zero, if voltage is at zero, you can see it here, voltage is at zero, it will result in a worst case condition. Highest amount of current will flow through the circuit, and the actual, we can say, the desired condition, when the DC decaying component is zero, the voltage wave should be at its highest. The maximum, the voltage wave should be at its, the switching should take place at the maximum of the voltage. In that case, DC decaying component will be zero, and the switching, if the switching takes place at voltage equal to 90 degrees, sorry, 0 degrees, not 0 degrees, 0 of the voltage, in that case, DC decaying component will have maximum value, or the total current will be 2 times Imax, that will flow uh, through the circuit breaker. I hope you understood this. Thank you.